Okay. Thank you for this nice introduction. So today I'll talk about the future of the LHC, and actually Mark Twain has once said it's hard to make predictions, especially about the future. I will try anyway. Okay, so just to remind you, LHC Run 1 has really been an enormous success. I mean, all of you are quite young and maybe don't appreciate it as much as I do, or people who are even older than me. I mean, it's been a very long time until we got to LHC Run 1. In the beginning, there were, of course, problems and so on, but in the end, this is just showing here the luminosity plot in 2012, and I think if we had known in 2008, if we thought that we'd have 20 inverse femtobarns at 8 TeV, we wouldn't have believed it. I wouldn't have believed it. Of course, earlier there was even more luminosity at higher energy. Anyway, so we got a lot of luminosity, 25 inverse femtobarn at about half the design energy, and of course we found the Higgs boson, which also, as we found at first glance, as far as we can tell today, it looks rather like a standard model Higgs boson. And we haven't found any physics beyond the standard model. In total, Atlas and CMS alone have by now already published 510 publications, I checked today. Okay? And these are actually half split between searches, so there have been about 250 searches for new physics and about 250 measurements of standard model processes. So what do we do in the future? So this shows the roadmap of the LHC. So here in 2009, we had the startup at 900 GeV. This is then what we now call Run 1, what I just talked about. So the instantaneous luminosity was 6 times 10 to the 33. And the spacing between bunches was 50 nanoseconds. So we collected a total of 25 inverse femtobarn. What we're now in, we're in this shutdown here in 2013, 2014, which is called Long Shutdown 1. Long because it's a 2-year shutdown. We have, of course, always brief shutdowns in between years, and during which the machine is upgraded so that we can finally go to design energy, or at least nearly design energy, probably like 13 TeV or so. And we go to nominal luminosity, which means 1 times 10 to the 34, so slightly higher than here. In order to mitigate the pileup, we go to a shorter bunch spacing, so a collision occurs then every 25 nanoseconds rather than every 50 nanoseconds. And the goal is then in this years 2015 through 2017 to collect an integrated luminosity of about 75 to 100 inverse femtobarns, so about 25 inverse femtobarns per year. At that point in 2018, there will be another upgrade to the injector in order to double or maybe even triple the luminosity once again, and to collect another 300 inverse femtobarns or so. And then in 2022, so this was always been the design of the LHC, to go to about 300 inverse femtobarns, and the detectors have been designed to sustain that. At that point, the detectors will have suffered significant radiation damage and also parts of the accelerator indeed. And so another upgrade is needed. And this is currently in the planning, the so-called phase 2 upgrade. This is called phase 1, this is phase 2. It's very confusing, actually, because these are long shutdown 1, long shutdown 2, long shutdown 3. And then there's phase 0, phase 1, and 2. So there's it. Yeah. So yeah, I even myself get confused sometimes. Okay. And so what here the plan is to increase the luminosity by another factor of about 2.5. And then over a period of 7 to 10 years to accumulate 3,000 inverse femtobarns, so to get a factor 10 more luminosity again. Just to, for this last point, for the high luminosity LHC, as I said, so the goal is to deliver 3,000 inverse femtobarns per year. So rather than rather than colliding all protons with each other, which would give us a peak luminosity here of 20 times 10 to the 34, 2 times 10 to the 35. This corresponds to very high pileup of like 500 interactions per crossing, which is experimentally difficult to handle. So what we do is we actually separate them a little, which is called luminosity leveling, so that Normally what happens, you have collide them all and then some disappear, and as a function of time, the luminosity decreases. With this luminosity leveling, we keep it at a steady rate of 5 times 10 to the 34 for a long time. At some point, there will be, enough protons will have collided, will be lost, so that then we get again into a decrease. So this is, in jargon, this is often, I mean, people call it luminosity leveling. It's already actually done currently for the LHCb experiment, because it doesn't cope well with very high pileup. So, and then what we will accumulate about 3 inverse femtobarn a day and 250 inverse femtobarns per year. Now, in order to be able to deal with this higher luminosity, the detectors need to be upgraded. And there is 2 primary reasons. One is that we have to significantly improve the trigger capabilities to better discriminate the events that we are actually caring about from background as early as we possibly can. And I'll talk more about this. This is the trigger is the enemy of the theorists, I always think. And then the other thing we need to do, which is rather expensive, is to upgrade and or replace the inner tracking detectors, partially because they cannot handle so high rate due to bandwidth limitations. It's just too many hits in too short amount of time that the bandwidth is too limited for this. They will suffer from radiation damage, which ultimately means that they become less efficient. And at this moment, they do not have trigger capabilities at early trigger levels, and so this would be good to put in, okay? So this is an upgrade, for instance, which is going on now in Atlas, a new pixel layer. So the current pixel detector is sketched here. We have here 3 layers, 3 barrel layers and 3 disks. And now we're inserting a 4th layer very close to the beam pipe at 3.9 centimeters. Otherwise it's 5. And so it's shown here. So this is here the beam pipe. This is this new insertable B layer, and this is the old pixel detector, okay? And using that, we will improve the tracking, vertexing, and beat tagging performance. So what's shown here is, for instance, the rejection. So we're setting our beat tagger, which I explained yesterday, to a 60% efficiency. And then we check how many light jets do we actually reject. For instance, for 50 pileup interactions, and you see with IBL, we're rejecting about 400, while without, we are rejecting only about 200. So we're improving the rejection by at least a factor of 2. And so this is being installed now. CMS is, for instance, building a completely new pixel detector, but not during this shutdown, on a slightly longer time scale. They want to install this in 2016, 2017. Again, also CMS want 4 layers. So this shows you the current one with 3 layers and the 4-layer detector here. And also one of the things that we always strive for is to build it with as little material as possible in order to minimize that the particles interact in that material. And again, by doing this, they get significant improvements in the beat tagging efficiency, or in the fake rate. And as I said, triggering is a huge challenge. This just shows the rate of triggers we've taken in Atlas in 2012 as a function of year, and then split here into the various physics objects. So for instance, we have 100 hertz of triggers we devote to electrons and photons, 100 hertz to muons, a bit more than 100 to jets, tau, and missing ET, etc. The challenge is, of course, that we have 40 megahertz collision rate, and we need to reduce this to of the order of a kilohertz. And we do this in a system which consists of 2 to 3 levels. And in particular, the first level is the most difficult thing to overcome. Here we have a bandwidth of 100 kilohertz, so we can accept 100 kilohertz at this very first level, which is a pure hardware trigger. And you see here the rate of such level 1 triggers, which operate with rather coarse information. So EM18 VH means that this is an electromagnetic tower in the perimeter with little hadronic activity behind it. And you see how this goes as a function of luminosity. So most of them just go linear because the physics rate increases with luminosity. But for instance, this one, XE40, this is a trigger that requires missing ET by 40 GeV. It has a quadratic term, so which is actually quite dangerous. So as the luminosity increases, we have to be more and more selective and cannot afford to waste bandwidth on background. And so this is what these upgrades are there for. So for instance, Atlas is trying to salvage single lepton triggers. This has the great advantage that there is a lot of model independent, so that the more selective the trigger is, the bigger the danger that we become already model dependent in which events we're writing to tape, which we want to avoid. By keeping a single lepton trigger, we basically avoid this. This shows here the lepton PT, the fraction of, for instance, WH events here in black as a function of the PT threshold. So you see, if you keep it at like 25 or 30 GeV, you keep 80% of WH events. You also see here a SUSY scenario, and this is a rather compressed scenario, and there you see the leptons are quite soft, so even with a single lepton trigger threshold of 30 GeV, you already have lost 80% of the SUSY events. So clearly keeping this as low as possible is desirable. In fact, at high luminosity LHC, just the pure rate of W events alone saturates the entire bandwidth of 1 kilohertz. So what we're doing is upgrades to several of our detectors to keep the trigger rate low. So I have a couple of pictures here. So for instance, at the moment, in fact, the blue ones here, this shows muons. Blue ones shows real muons that have been found both in the muon spectrometer and in the inner tracker. And these hatched areas shows at earlier levels. This shows what all we're triggering. So you see that currently Atlas is triggering on a lot of things at high eta which aren't really muons and which we reject later on. So by installing a new muon detector, we mitigate this. Similarly here, for the calorimeter at the moment, if we just have the black just shows the rate for electrons with ET greater than 34, and the blue shows what we can do after upgrading our system, and you see that that we reject a vast majority of these electrons, which are primarily not interesting physics-wise. This just shows from CMS, also planning trigger upgrades. This shows the efficiency that at trigger level we have for a variety of Higgs processes. So here, for instance, WH going to E nu BB bar. So with the current system, we're writing about 40% of these events to tape. And with the upgrade, we can go up to 70%, improving the acceptance by about 70%. For taus, it's even more dramatic, from currently only about 15%, going all the way up to 50%. Okay, so this is very important, and this means that not only will we have more luminosity, which will improve the precision of these measurements, but we also have better detectors that further improve these measurements. Then finally, there is the phase 2 upgrade. So all of what I talked before was going to happen before 2018. Now this is planned for 2022. So this is the most expensive. The tracker upgrade, that alone costs, depending on how you count, well, so like $500 million, okay, if you include manpower. And it's because we're building an all-new tracker here, basically a new pixel detector, a new strip detector here, and with higher segmentation and more layers before. Again, in order to be able to cope with the very high luminosity we expect at that time, and to ensure, for instance, that our B-tagging performance is still then as good as it is now, or even better. CMS does the same, of course. So CMS has also a design for it. CMS has, interestingly, has a new idea of putting a ton of pixel disks in the forward region. The idea would be that you could that way, at the moment the tracking is limited to eta less than 2.5, and for processes like vector boson fusion, maybe it's useful to confirm jets with tracks in the forward region, and so this gives this possibility. Okay. That was very experimental stuff, I apologize. But so there's a lot of work, just to give you an idea. I mean, so there is a huge amount of upgrades planned, and of course they take a lot of resources also. But they're important in order to keep the physics capabilities as they are now. Okay, so let's come to the very near future. So run 2, this is in 2015. So what I show here on the left-hand side, this is the ratio of luminosities for 13 TeV compared to 8 TeV in blue. And you see that for 100 GeV particles, or for the Higgs, this ratio is about a factor of 2, while then as you go to higher and higher masses, this ratio increases and increases most dramatically for glue-initiated processes. So for particles with masses of the order of 2 TeV, the cross-section increases actually by a factor of 10. And so already with a few inverse femtobarns of 13 TeV data, we actually open new discovery windows for such very heavy particles. This here on the right shows you the ratio for 14 over 8 TeV cross-section for a variety of processes. So here on the left you see the Higgs processes, and then here you see SUSY, for instance, with stopped quarks of 500 or 600 GeV, where the increases of the order of 6 or 7. And then the most dramatic you get, but this is, of course, when you have, for instance, black holes of 6 TeV, you get a factor of 10,000 increase in cross-section. So with this, we also will be able, in this run 2, we will basically have a factor 3 larger cross-section for Higgs production, and we'll have a factor 5 more data ultimately than we have now. And so basically during this run 2, we expect the precision of the measurements to improve roughly by a factor of 4 compared to what we have now. Okay, and then beyond run 2, so there have been a lot of studies recently. So for a center of mass energy of 14 TeV for integrated luminosities of 300 and 3000 inverse femtobarns. And there have been different approaches by Atlas and CMS to do that. So Atlas has basically parameterized the detector response using functions, analytical functions that smear, for instance, the jet response, or that apply an efficiency that we expect there to be. In fact, this has been rather, Atlas is always a rather conservative experiment, and it was based on, we now know that these have been quite pessimistic, these assumptions. So we think we can do better than we projected here, but, and we will update the studies, of course, but these things take time. So for instance, the B-tagging and missing ET performance was already found to be better than we assumed at the time. CMS has taken a different approach. They've simply extrapolated the current analysis, knowing the cross-section at higher center of mass energy and the higher luminosity. And they've just assumed 2 scenarios. One is conservative and one is aggressive. So scenario 1 is where, well, so the whole art in this, actually the whole art of being an experimental physicist altogether is to determine a systematic uncertainty, pretty much. And what's really hard to know is how such systematic uncertainties will improve in the future. Because you use data to constrain it, it's very difficult to assess them there is no rigorous way usually to assess them. So it depends on the techniques you have available, the tools, etc., and how well the data actually agree with, for instance, the Monte Carlo generator in a given distribution. So what CMS is assuming that they, conservatively, they just say, well, we will do them as well as we can do now, okay? And so this is basically maybe things become harder because of pileup, but we'll also get smarter, and these things compensate exactly. And also, they have, in this scenario, assumed that the theoretical uncertainties, which, as you see, are quite important, will also not change in the future. Then there is scenario 2, which is much more aggressive. Here, CMS assumes that the systematic uncertainties improve as square root luminosity. So this is basically like the statistical error. So this assumes that you can learn from the data, and many of the systematics are driven by data statistics. And they have also now a lot of faith in the theorists that the errors can get reduced by a factor of 2. Okay? So the truth is probably in between these 2 scenarios. So this gives a range. Just to comment on how, assuming that systematic uncertainties indeed scale with squared luminosity is certainly not crazy in my opinion. What I'm showing here is the top mass uncertainty as a function of integrated luminosity at the tevatron and the W mass uncertainty, okay? And it shows the total error, which is composed of the statistical and the systematic error, and you see in both cases, so what the dashed line here shows and the red line here shows an improvement just with square root luminosity. And you see with the W mass that it exactly holds. The measurements were all exactly on this red curve. This is the best measurement to date from CDF. And here in the top mass, it also very nearly held. So, and the reason is that once you have higher and higher statistics, you're able to select kind of the best measured events, and you also are able to use the data to constrain systematics in situ. Let me just show you a little bit what pileup then does at 140 or 200 interactions per crossing. This shows here the jet resolution. So the black is if we didn't have any pileup at all as a function of the jet PT, and then these colored curves are different pileups. So the blue here, for instance, is for 140, and you see that there is a significant degradation by about 30% in the jet resolution at low PT. At high PT, it's not so bad, yeah? So it's less, but at low PT, and so this is important, for instance, for low mass dijet resonances like Higgs to BB bar. This is a concern, and we need to work hard to try to further improve it as much as we can. Similarly here for missing ET, so this shows the missing ET resolution here in GeV as a function of the total energy in the event. And you see here, for instance, for 4,000 GeV of total energy in the event. So this is about 60 or so at low pileup, and it's about 80 or so at high pileup. So it increases, but not super dramatically. And one can consider this is certainly manageable. Yes?
Can you explain why the trend of this missing T constantly in this red part?
Sorry, what?
Increase as you increase the missing T.
Ah, right. Yes. So the missing ET actually, it depends on how much there is in how much ET there is. So if the more energy you have, the more energy you can mismeasure. Okay. So this is for events which don't have any genuine missing ET. But then the more energy there is, the more, which is here the observed energy, the more you can also mismeasure it. So the missing ET resolution actually, missing ET resolution strictly scales with the missing ET divided by the scales with the square root of some ET. So that's basically the fluctuations in the sum ET measurement are approximately square root sum ET, and so that defines how much missing energy. Yeah, well, I mean, it's basically, this is 80 divided by 4,000, yeah? Because there is no, so the thing is that there is no real missing ET in these events. So this shows just how much we get from mismeasurements. So the central value is 0 on average for the missing ET. Yes, Z prime to ttbar. But it's an all hadronic ttbar. Yeah. So there's some because of the B jets. The other thing, a concern one might have is, I mean, as we go to higher center of mass energy, of course, these boosted techniques that you heard about are becoming more important, and one might be worried that as we go to this very high pileup, these might not work anymore, okay? And indeed, if we don't do anything and just take a fat jet, which I've done here, so this is for Z prime decaying to TT bar, and I take a fat jet of 500 GeV or so with a cone of 1 and look at the mass of that jet. So the black shows for no pileup, where I see a very nice top peak, and then as you go to higher and higher pileup, the peak smears out and moves to the right. So that at 140, it's at 280, which is very far away from the true top mass, of course. But once you do trimming, as if, yeah, then it all works again. So you see that it even with 140 pileup interactions, you nearly recover the performance that you have without. You don't quite. It certainly has a worse resolution, but there's certainly still a very nice peak that one can work with. Okay. Now let me also comment on theoretical uncertainties. So this is critical for us for two things. One is to estimate the cross sections of background processes or signal processes and the other is also to estimate the acceptance of our signal process. Typically, there are, of course, missing higher order QCD corrections, and these we estimate by varying the renormalization and factorization scales. There's typically electroweak corrections, which actually, for high mass processes, can be quite significant, up to 20% or so. And another uncertainty, which we always have to live with, is, of course, on the parton distribution functions. However, there are efforts to use the LHC data itself to reduce those in the future. In particular, the acceptance is very important. So the Higgs analysis, so for instance, the Higgs to WW analysis requires, it works in the zero jet bin, right? So it requires there to be no jets above some value. Or also the gamma-gamma. I mean, now that we're studying the Higgs, we're really doing this basically in bins of number of jets, because we also try to separate out the gluon-gluon fusion from vector boson fusion, etc. And so in order to understand this, we need to understand which fraction of Higgs bosons have 0, 1, or 2 jets, etc. So, and in order to understand that, we need to understand, well, the Higgs PT distribution. Here I just show a plot from the LHC Higgs cross-section working group report, which just came out earlier this month. And it compares here, for instance, many of the state-of-the-art Monte Carlo generators, so most of them here working at next to leading order, in fact. And you see that the Higgs PT distribution, they are in kind of some reasonable agreement, but there are certainly differences here. For instance, MC at NLO, AMC at NLO is certainly harder, for instance, than the other ones. And so this directly, I mean, if we take, for instance, the spread of these generators as an uncertainty, this directly feeds into the Higgs cross-section uncertainty because we have a jet Vita requirement. This is just a slide from John Campbell about the uncertainties on Higgs production at 125 GeV for the various processes. So, for instance, for the glue-glue fusion process, the uncertainty is about 15%, and it's about equally split between uncertainty due to higher order corrections and due to PDFs and IFIs. ttbar H also has a large uncertainty similar, and then the vector boson fusion WH and ZH have significantly smaller uncertainties, and primarily actually PDFs. Here the high order corrections are small and very well under control. So we, I'm just saying because you're the theorists of the next generation, so we need some theorists to work on this. How many of you are working actually on model building? Okay, and how many of you are working more on something like this? Okay, some also, that's good. Okay, well, we need the model builders also, I'm not saying, I mean, we need a large variety of theorists. Okay, all right, so let me then talk about the measurements we'll do in the future about the Higgs boson. So the mass, we will already achieve a precision of about 100 MeV in run 2. And this will be difficult to improve afterwards. And as far as I understand, that's pretty much, that's good enough also. The width is expected to be very narrow for the Higgs, and we can, if it is that narrow, we won't be able to measure it. We can set upper limits on it, and there is a first direct upper limit, but it's like 6 GeV, which is not particularly interesting compared to the actual width of it, which is more like MeV. Already, also the spin and the parity we have already pretty much established to be 0+, but we will investigate CP violating contributions. That's interesting. But what is particularly interesting is really to start now this program of measuring couplings to fermions and bosons as precisely as possible, because new physics can come in loops here, and which would modify these couplings, for instance. So what we actually measure is this quantity mu, which is the cross-section times branching ratio we observe in the data, divided by that predicted in the standard model. That's what we actually measure, but then making a lot of such measurements in a variety of processes, we can put them all into a fit where we let all the coupling parameters float and interpret, well, basically then interpret these measurements in terms of couplings. And this is, and so since there is this always, with respect to the standard model, this is where there is a direct, so this is where the theory error, of course, enters directly. The more precisely we know this, the more precisely we know mu. And as the data precision improves, the more important it is that this goes down. So these are the production processes that are studied, and then what we do is, in order to quantify these couplings, we just, wherever there is a Higgs coupling, we insert a kappa, which has a value of 1 in the standard model and can have any non-1 value otherwise, okay? So it's just a scaling factor here. And then we, for instance, this process and that process, these both constrain kappa t, okay, the top coupling. And then we have the decay, of course, where, again, the same kappas appear. So let me just remind you briefly of run 1. So this is the measurement here that we currently have of the Higgs boson mass. They're consistent between ATLAS and CMS, and the uncertainty is about 500 to 600 MeV. As I said, this will go down to 100 MeV in the next run. And then this is the start of, this measurement of mu for ATLAS here and CMS here. So you see that the best measurements at this moment have an uncertainty of about 20%, while the worst ones, I mean, so the least precise ones have still an uncertainty of like 60% or so. So this is, for instance, here Higgs to BB bar in both cases. And also Higgs to tau tau. They are still quite limited in precision. And this shows here a plot. Sorry, it's kind of cut off. This is the confidence level. This basically is a plot illustrating where that we have now rejected any hypotheses we've tested, so which are 0 minus, 1 plus, 1 minus, and 2 plus. We've rejected all confidence level, mostly at more than 99% confidence level. And so using these measurements, we've extracted first couplings. So this is here from CMS, for instance. So this is the inclusive coupling to vector boson, inclusive coupling to fermions. Then this is the ratio of the W to Z couplings. This is the ratio of down to up quark couplings. So this is, for instance, very interesting. And you see here the precision is still quite limited, okay? And also the lepton versus quark couplings, the precision is still quite limited, while the inclusive coupling to vector bosons is already known, so the red is here the 1 sigma level, it's already known basically to 10%, okay? So what can we do in the future? So this shows then the future projections here. This is from CMS for the diphotons, ZZ, WW, tau, tau, and BB channel. So you see in green is what we have now, or we had at the time with 10 inverse femtobarn last summer. So where it was between 50 and 70% or so. And here you see that with 300 inverse femtobarns, so the red shows, so the black shows purely the experimental uncertainties. And you see that there pretty much everywhere we get to an uncertainty on mu of 10 to 20%, which, as you'll see, is actually half on the coupling in the end. And you see here that, and then in red you see what you have if you have both theory and experimental uncertainty. So you see in the Higgs to gamma gamma case, the theory uncertainty will already completely dominate. That's why I was talking a lot about the theory uncertainty. And this here shows from ATLAS now for a larger number of processes and decays, for instance, also Higgs to mu mu. Again, the 300 in green and 3000 in blue. So you see that there is, so with 300, for many processes, we go below 20% to 10 to 20%, although there are some rare processes where we're still limited to about 50 to 60%. And in these cases, this is where really the 3000 inverse femtobarn high luminosity LHC gives us a huge gain of a factor of 3 or so, so that nearly everywhere we go to 20%. There are some outliers here, the VBF Higgs to WW, but this is where we think we were really far too conservative, and in real life we think that we will be significantly better than this. And again, the hatched is theory plus experiment, and the non-hatched is just experiment, okay? So that's where you can help. BB bar, okay, so yes. So ATLAS has not made a BB bar projection. And the reason is that we were not, we did not feel confident enough to parameterize the jet resolution. At the time, we only had Monte Carlo up to pileup of 40, and we knew there's a strong dependence on the pileup, and so we didn't dare at the time. But it is a very high priority to come up with this because, of course, Higgs to BB bar is a very critical branching ratio to measure. Actually, there's been recently also a paper on an idea on how we can measure Higgs to charm, to constrain even the Higgs coupling to charm quarks at the LHC via J-psi photon events. Other than one has to understand J-psi production, which is not easy. Okay, so then we have all these measurements, and then we can take ratios of them, for instance, and that way we can already constrain ratios of partial width. So for instance, here this is the partial width to tau over that in muons. Again, so you see that with 300 inverse femtobrons that we are only sensitive to 60% or so, while we're really probing that to 20% level once we are using the 3000 inverse femtobrons. And this shows here from CMS again. So these are now these two scenarios that I discussed before, the conservative and the optimistic. And you see with 3000 inverse femtobrons, basically all couplings here to photons, vector bosons, gluons, Bs, tops, and taus are then optimistically measured to better than 5%, between 1 and 3%. So that's very nice. Particularly interesting is that we are then sensitive to new processes that we will only really see with this very high luminosity. So here I'm showing you the current limit on Higgs to mu decays, where currently we are, the limit is about a factor 10 higher than the standard model. So in order to become sensitive, indeed, we need a factor of 100 more data to first order. And this shows here a study with 3000 inverse femtobrons. So here you see we would be able to extract such a peak on top of this huge Drell-Yan background. That's the problem here. So first of all, the coupling, of course, to muons is very small, but also there is the Drell-Yan background that we need to extract this signal of. But we expect to have a more than 5 sigma significance then, and to actually measure the coupling to muons to 10 to 15% precision. Similarly, other ones, so for another rare process is Higgs to Z gamma. So there also we have currently, we're about a factor 10 above the standard model expectation. There aren't any future studies yet on this from either collaboration, but you can, I mean, it's based on the Higgs to mu studies, and because also experimentally it's extremely clean because we let the Z decays to leptons and the photons, so we have a very narrow mass peak, as you can see here. We expect also again to have then sensitivity at the level of 15% or so with the high luminosity LHC. And of course there's maybe other rare decays we haven't studied yet. Another area is weak boson scattering. As you know, in the standard model, the cross-section for longitudinal WW scattering increases with energy, and in the standard model, this is cancelled by the presence of the Higgs boson, which cancels these terms. It's, of course, very nice to test this experimentally to see whether it really works, and also or whether maybe there is some strong dynamics still contributing to these interactions. And so this can be done. So one looks for pairs of vector bosons. Atlas has studied ZZ-WZ and also like sign WW production. And then you see here, so this is, for instance, the 4-lepton mass in ZZ production. And you see here the backgrounds in orange. Then this blue is the vector boson scattering signal. And then if there is some anomalous coupling contributing to it, then you might get this harder spectrum here shown in red. And similarly here for same sign WW scattering. What is important for these processes is that there are forward jets in these events which we can tag experimentally. So using a framework of effective operators to parameterize these new physics, we get then here these, we can probe a variety of operators here, 6 and 8-dimensional ones, for instance, and you see here the constraints. So we typically, going from 300 to 3000 inverse femtobrons, we improve these significantly by a factor of 2 to 3. Then, of course, then there is a completely different question about the Higgs, which is what protects the Higgs mass from being higher. And there is a lot of possible answers to that. One is that you have supersymmetry with a top quark with a mass less than 400 GeV or so. And I already showed this from Nima here yesterday, and I'm sure you heard about this before. There's an alternative is that you could have vector-like top quarks, or you could, of course, have some other dramatic new physics coming in at a mass scale of a few TeV, or the weak scale is very fine-tuned. And so we can look for these, of course, directly, and already did this in Run 1, and so now just discuss how much better we can do this later. So we have this direct, so we can study top quarks either via direct production diagrams like these, or from Gluino decays if the Gluino mass is low enough. And then typically they decay via charginos or top quarks, the W's and B's. And so this shows the current constraints on the top quark again. So this is for the case where it decays either into top and neutralino or into charm and neutralino here. So there's a very significant, so the bounds go up to 700 GeV or so, but as you increase the neutralino mass, there is still room here. And here in the Gluino mass, we're basically probing up to 1400 GeV, and here up to LSP masses of 600. And this is a big program, and these constraints are ever improving. However, at the moment, they're still very natural scenarios are still perfectly allowed by the data. So for instance, I put here the star at a 1500 GeV Gluino with a stop mass of 300 and LSP mass of 150, which is just a very nice, could easily be true, would be very natural. And so this is where, of course, with higher luminosity and future running, we can further probe this. So this shows an example, for instance, the Gluino reach in the case where it decays via top quarks or bottom quarks. So this black here, so this is based on a same sign Dilepton analysis actually. So the black shows the current constraints from CMS in this case going up to 1.1 TeV. And once you go to 300 inverse femtobarns, we're going here nearly to 2 TeV, okay? And this is the discovery reach, not the limit, okay? Well, the limit will be, of course, better, but hopefully we'll find it, so then we don't need to worry about the limit. And then similar here via bottom. So we're basically able to discover Gluinos up to 2 TeV in such scenarios. Similar for the top squark. So here we are able to make discoveries up to 800 or 900 GeV. And with the full 3000, even already with 300 inverse femtobarn, and with full 3000, we can make them up to 900 or maybe even 1 TeV. And also, actually, it's important to point out also here in this dimension, in the LSP mass, we improve significantly. Currently, it's basically 150 to 200 GeV, and we go up to 400 GeV. And then another, it of course is quite possible that there is fine-tuning, and so the squarks are all heavy, and the stop also, but there's still other reasons that there could be the masses of SUSY particles could be low, for instance, dark matter unification of couplings. So one very promising search is the search for charginos and neutralinos. So this is completely independent of what happens with the leptons and squarks. Would decay, for instance, into a W or a Z. I'm sure that Sunil talked about this. And the current constraints are actually rather weak, so we're constraining up to chargino masses of 300 GeV, but only for the case where the LSP mass is below 100 GeV or so. And so here we have a very dramatic improvement with 300 inverse femtobarn already extended out to 500 and doubling the LSP mass reach, and then with 3000 really covering nearly up to a TeV and up to 300 GeV. Another search is that for generic squarks and Gluinos. So this is a classic search I talked about, this inclusive jets plus missing in T search. As I showed you yesterday, this is very complex. There we look for 2, 3, 4, 5, 6 jets, and then we have a variety of 7 actually also, and up to 10 jets. And we have a large number of signal regions to fully optimize. When we do these feasibility studies, we don't do it like this because we're just getting an approximate handle on it. So we just optimize basically in one variable, which is the effective mass. And so this shows here the effective mass distribution for Gluinos here of 3 TeV in blue and the red, and then for these backgrounds, okay? And using this, we can see here where we end up. So the solid lines are the discovery reach. So in blue is for 300, and in red is for 3,000 inverse femtobarns. So you see, in terms of, this is the Gluino mass here and the squark mass here. So the Gluino mass, the discovery reach goes up to 2 TeV, as I already showed you for the third generation heavy sample. So it's up to 2 TeV with 300 and up to nearly 2.5 TeV with 3,000 inverse femtobarns. Okay. And yeah. So as I said, another option is that there is no supersymmetry, at least not at the weak scale, and instead we might have vector-like quarks. So these are colored spin 1/2 fermion, which transform the same on the left and right-handed, for left and right-handed ones under the electroweak gauge group. And so we have processes like this, where we have these vector-like quarks produced, and they decay via an electroweak boson to an ordinary quark. There's a rich number of signatures and actually also rather complex limits plots nowadays being produced. So this shows an example here. So this shows here on this axis the branching ratio of the top of this vector-like top going to a Higgs and an ordinary top quark. And on this axis here, the vector-like top going to a W and a B. But, and then we have 4 analyses here, which in this plane come in different ways. So you see here the blue, this is the search for top Higgs production. It comes in, it's mostly sensitive when this branching ratio is large. Okay, so it's in this upper right-hand corner, while then an analysis which targets WB is mostly here on the right, etc. And so at the moment with the current data, we're sensitive. You see that basically the 600 one is nearly completely filled out, and then it's getting kind of quite scarce beyond 750 or 800. So we're sensitive at the moment between 600 and 750, depending on exactly what its branching ratios are. So in the future, we can push this to about 1.5 TeV already with 300 inverse femtobarns, and we don't have the projection for 3,000, but probably like 2 TeV or so. So typically, I know these are a lot of numbers. So typically, so this is about, so 1.5 TeV is about a factor of 2 compared to what we're probing now, and that's very typical. Okay. That we increase the reach by about a factor of 2 from where we are now to what we can do with phase 1 with 300 inverse femtobarns. There's a lot of other new particles that could exist, so this is the current constraints on them. So here, extra dimensions, leptoquarks, excited quarks, etc. So mostly they range from a few hundred to a few TeV. So we have a couple of examples. Of course, making projections for all of them would be a bit excessive. But for instance, for ttbar resonances, we did this. So this shows here this is in lepton plus jets event, the reconstructed ttbar mass distribution for a 4 TeV Kalut-cycline gluon. Compared to the background estimates with 3,000 inverse femtobarns. So what we expect is we will be able to, actually, it's not always trivial to understand how the mass reach changes. What's much easier to understand is usually how the cross-section limit changes. And this typically, so with the factor, with the extra center of mass energy and the improvement with luminosity, we will be able to improve the cross-section times branching ratio limit by a factor of 100. So at the moment, it's about 0.1 picobarns, which would be here, and with 3,000 with femtobarn, we'll go nearly down to a femtobarn limit on such processes, okay? And then there is here for a given given theoretical scenario, one can understand what this means then in terms of mass reach. And you see that currently we're probing here about 2 TeV particles, and we're going to go to 3 to 4 TeV with 300 inverse femtobarns and 5 to 7 TeV with 3,000 inverse femtobarns. So it's very significant improvement. Similarly, another classic search is that for Dilepton resonances. So again, currently we're constraining this already at the level of about 0.3 femtobarns. And again, we expect an improvement by about a factor of 100. So we're going to go down to nearly attobarn level here. 10 to the minus 6 is an attobarn, so below 10 to the minus 5 picobarns. And so at the moment, we're probing for this toy scenario where we assume that the Z prime couples to fermions exactly like the standard model Z prime, the standard model Z. For that, we currently constrain to 2.5, 2.8 TeV, and these constraints, I mean, so we will probe up to about nearly 8 TeV in the future on this. Last but not least, there is also the study of the top quark. So in the standard model, the top quark decays nearly all the time to WB. So flavor changing neutral currents are very rare in the standard model at the level of 10 to the minus 14, 10 to the minus 16. So seeing the top quark decay in any of those ways would be a very unambiguous sign of new physics. So this is basically similar to, this is the intensity frontier of the LHC here, to probe these very rare couplings here. And so in many models of new physics, these are significantly enhanced. They are still small numbers, but you can see that there is 10 to the minus 4, 10 to the minus 5 is appearing all over this table. So this is really a very interesting range where if we can get to probe them at this level, this could be an interesting first sign of new physics. And so this shows here what we can do. So this shows for the branching ratio of top going to quark Z. Actually, what is missing is what can also happen is top going to up Higgs, for instance. So these studies are now starting. In fact, the first results on this were presented this week at a Higgs conference from Atlas. But anyway, so at the time, we only had quark Z and then also quark gamma. And so at the moment, the limits are here in the range of a few times 10 to the minus 3. And we can push this down by nearly 2 orders of magnitudes with the full 3,000 inverse femtobarns going, indeed probing then the range well below 10 to the minus 4, down to nearly 10 to the minus 5. Okay, so I'm nearly done. So just one more thing. So the good news for the high luminosity LHC or the LHC program in general is that last year there was CERN convened the so-called European strategy to plan for the future of particle physics in Europe. And it was decided that Europe's top priority should be the exploitation of the full potential of the LHC, including the high luminosity upgrade of the machine and detectors, with a view to collecting 10 times more data than in the initial design by around 2030. This upgrade program will also provide further exciting opportunities for the study of flavor physics and the quark-gluon plasma. And so at the moment in the US, there is the SNOMAS process ongoing, followed by a P5 panel, which also will suggest then funding priorities. So I wanted to ask you some questions. So I showed you what we can do with so much more data. And one concern that is also often voiced is, do we have to actually decide now what we're going to want to do? Of course, the lead time for constructing something like a completely new tracking detector is large, though. So basically, in order to have it ready by 2022, has to start construction in 2017. And you need to already, before you start construction, you need to know exactly what you're going to want to build and do a lot of testing and R&D, of course. So there's a significant amount of money already required before in order to get to that. So the question one could ask is, well, can we just wait what we see with with Run 2? Can we just wait until we've seen, 20 or 30 inverse femtobrons of run 2 data before we have to commit to what we want to do in the future. Well, the Europeans have already committed, but so we could just go through a couple of scenarios what might happen, okay? What might happen, let's say, in the first 50 inverse femtobrons, which we might have analyzed by 2017, let's say, by Morion 2017. So of course, well, so this scenario A is my favorite, that we found a 5 sigma axis in data in at least one beyond standard model signature. Okay, so what do we do then? Build, okay, fine, exactly. What do we do if we just see a 3 sigma axis? 100 TeV. And then there is, of course, so we could have, then there is the possibility, I'll talk about 100 TeV in a moment, actually, I have some slides, that we found no axis in data greater than 2 sigma, but we see a deviation in the Higgs, in one of the Higgs coupling measurements or in Higgs signal strength measurements of by about 3 sigma. And then there is also scenario D, which is that we don't see any axis in the data and we don't see any deviation in the Higgs in the Higgs couplings either. So do you think there's any scenario where we wouldn't want to go all out on this program anyway? Let's just be honest. Who thinks you want to build it? I have to give a talk at SNOMAS next week, so I'm also trying to get the arguments together and see what you think. I'm picking your brain here. So who thinks that there is at least one of these scenario means that you just don't want to build it, you want to stop the program? Okay. Sorry? Yeah, well, that's okay. Yes, that's. But I mean, this is why it's nicer to commit before, because then. I mean, the question is, you need to. I mean, so whether you can build something better for that money, right? ILC was, but that's a factor 10 more expensive. So, NLC? Well, yeah, okay, but now, yes, but in Japan, so that's more expensive, right? But yeah, so you think that we should, if we see nothing here, we should build them? No. Okay. Anyway, it's a difficult. Well, so who thinks we should go ahead regardless of A through D? Okay, that's the majority. All right. Thank you. I think so too, because, I mean, well, first of all, I actually personally think that this, I mean, it's unlikely because there's always going to be some excess somewhere. So we'll probably have some deviation which may turn out to just be statistics in the end, but we would want to follow up on, right? Okay, so then what about then the further future, the far-ish future? So one idea is that one could reuse the LHC tunnel and equip it with stronger magnets. Currently, what limits the LHC energy is the strength of the magnets. It's 8 Tesla magnets, and there has been a lot of R&D on improving that. There is 20 to try to go to 20 Tesla. I think 15 Tesla has actually been achieved, but the goal is to go to 20. If you went to 20 Tesla magnets, you would be able to have an energy of about 33 TeV in the LHC tunnel. Okay. So the problem with this is that once you've run the LHC for such a long time, it's not clear how you can take out all the magnets because they will have suffered a lot of radiation on the way, so whether you can take them all out and put new ones in. So this is the, yeah. Another idea is, so this shows the CERN site. So this shows here the LHC ring. This is here the Lake Geneva. Here you see the airport. And here are the Jura Mountains. I live over here. Okay, so and this is also another mountain, the Salève. So one idea is to put in a new accelerator, which is much bigger. This is an 80-kilometer ring here, which uses then the LHC as pre-accelerator. Okay, so this is a feasibility study here, or some people would prefer. For instance, Nima told me yesterday he would prefer 100. So, so this is 100. So that's another idea. Okay, so there are honestly studies going on about the civil construction, what you could do. So here the circumference of 80 to 100 kilometers, then one would still use these strong magnets that I just talked about, which are with fields of 20 to 16 Tesla. Yeah, okay, so the injection energy, this comes from the LHC then. It's up to something between 3 and 7 TeV. And what you then achieve with these parameters is that you can get to a center of mass energy of 100 TeV. The luminosity, again, would be similar as what's planned for the high luminosity LHC. What is difficult is that this is an enormous energy, so this, yeah, so there's a lot of challenges here. Anyway. What? Which number? Ah. Yeah, I don't know the price. But yeah, so as I said, so there is, for instance, now just on the civil construction, there is a study ongoing, and so they are evaluating the price of that for sure. Yeah, it's not cheap. I don't know how it will compare to the current LHC, right? Okay. So let me conclude. So Run 1 has been a fantastic success where we found a Higgs boson. We put very severe constraints on physics beyond the standard model and published more than 500 papers on a very broad range of topics. That's why if anyone asks me about a given one, it's really, you know, it's kind of luck whether you know this particular one or not. It's quite hard to keep even track of all this data pouring out of the LHC, even for someone very strongly involved. However, the knowledge of TeV scale physics will be improved dramatically by going to by future LHC running. So we're going to go to the full energy, which is nearly a factor 2 increase, and we're also going to increase the luminosity by about a factor of 100. And this will allow us to make Higgs precision coupling measurements really with a precision ranging between 2 and 10%, and to search for new particles with masses up to well, so to extend the mass reach that we currently have by about a factor of 2 to 3, depending on the particle. Theorists play a very, very critical role in us exploiting the LHC by either making precision calculations that help us achieve this precision, or by pointing out what we should be looking for instance. High luminosity LHC then significantly improves upon LHC and is considered a top priority in Europe. And as I just showed you at the very end, there's also higher energy options that are being studied, and R&D is going on in this area. Thank you.